Hi everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about PN junction and the current voltage characteristics of a PN junction. This is the second topic in the module semiconductor devices. The last class we have already discussed about direct and indirect band gaps. And those of you who have not seen can refer to this video on direct and indirect band gaps for continuity. So let us see the brief outline of today's topic. First, we'll see the introduction of PN junction, means what a PN junction exactly is. And then we'll also discuss the methods of the formation of a PN junction. What are the different methods that are available for the formation of a PN junction? And then we'll see different phenomena, that is diffusion of charges. These are very important definitions. Diffusion. And then the generation of electrical field, how electrical field arises due to separation of charges. And then also we are going to discuss about the depletion layer and the potential barrier. Then we'll also see the drifting of the charges and the drift current that arises due to drifting. And finally, we'll discuss about the voltage current characteristics of a PN junction. So let us first discuss what a PN junction is. A P-type semiconducting material is placed with an N-type semiconducting material. So if you see in the figure here, this is a P-type material. We are taking P-type silicon, and this is N-type silicon. So P-type material and N-type material. How they are placed? They are placed in such a way that the atoms of P-type combine with the atoms of N-type across the surface of contact. So this is the surface of contact. So across this surface, the atoms of the P-type and the N-type will combine. And such a junction, we are calling it as PN junction. This junction is known as PN junction. Now, how this junction is formed? In practice, if you see, there are different methods, and we are going to discuss about three methods that are used generally for the formation of a PN junction diode. The first one is the grown junction type. Second is fused or alloyed junction type. And the third one is diffused junction type. So we will see in detail about each method. First is the grown junction type. So in grown junction type, what we do is take an extrinsic semiconductor and it is grown from the melt. What is an extrinsic semiconductor? When we say extrinsic semiconductor, it is impure semiconductor. It is impure. Impure means either you can add a trivalent impurity to get P-type, or when you add pentavalent impurity, you get N-type. So they are extrinsic semiconductor. So we will grow an extrinsic semiconductor, either P or N. It is grown from a melt. You will take it in a molten state and try to grow. Now, during the middle of the growth process, when suppose if you are taking a P-type and growing, then impurities of the opposite kind, means for P, N will be the opposite, and for N, P will be the opposite, are added to this melt, so that the opposite type of crystal grows further. So I hope it is clear. When we are trying to get an extrinsic semiconductor from a melt, first we take one type of material and grow the crystal, and later on we will replace it with opposite kind of material and then grow, so that you will get a PN junction. Now let us see the example. So here, if you see in the diagram, you can see that's a crucible we have taken, and this is in a molten state we have taken. Suppose N-type silicon is grown in that. We are pouring the melt with the help of this funnel. So now when N-type silicon crystal containing phosphorus atoms as pentavalent impurity are grown, the growth process is stopped temporarily and efficient boron atoms are added to the melt as trivalent impurity. So first we have taken N-type, that is phosphorus atoms. We will let the phosphorus atoms grow till here, and now we will start adding boron atoms. Boron means trivalent, so it becomes a P-type. So now when you start adding the melt, so on this what you get will be a P-type. So that is how we get a p-n junction. So this results in the growth of a P-type thereafter. Now the second method is fused or alloyed junction type. So in fused, P-type and N-type materials are kept in contact and then they are fused together by proper heat treatment to form the junction. So let us see the example. See the diagram. What we have taken here is a P-type germanium wafer, and then we have this indium dot. Indium is P-type, and then if you are taking, then this should be N-type. Okay, this is the indium dot, which is P-type, and that is placed in contact with N-type material, or we are calling it as a wafer. So a small dot of indium, that is P-type material, is pressed on a thin wafer of N-type material, that is N-type germanium. Now during few minutes of heat treatment, I told you in fused we use the heat treatment, the indium atoms fuse into the surface of germanium and they produce a P region inside. So when you are heating it, these P-type atoms will fuse inside. Like you see here, they have fused inside this wafer of N-type material. So they are producing this P-type inside germanium. So this P-type region with N-type germanium wafer forms a p-n junction. This is how using the fused method we get a p-n junction. Now coming to the third type, that is diffused junction type. So diffused junctions are formed by impurity diffusion technique. So we are going to diffuse the impurity atoms. What is diffusion first? It is a process of movement of charge carriers always from a higher concentration to lower concentration. From higher concentration side, they move onto the lower concentration. And this diffusion process may be either gas diffusion or we may use solid diffusion method. Now let us see the example. In gas diffusion method, a wafer of N-type silicon is heated at about 1000 degrees Celsius in a gaseous atmosphere of high concentration gradient. I told you in diffusion, we try to maintain a difference in concentration because always the atoms are moving from higher concentration to lower concentration. Now at that temperature, that high temperature around 1000 degrees Celsius, due to the concentration gradient, what happens? The boron atoms will diffuse into the N-type silicon, forming a p-n junction. So here if you see in the diagram, a p-type impurity, say indium, is painted on an N-type substrate and both are heated. So this is N-type silicon or germanium and this is indium, which is p-type. This is kept and now we see it in the molten state on heating. Then what happens here is these atoms will diffuse, whichever is higher in concentration, they will diffuse into the other type of material. So here we have the p-type and here we have the n-type. Now when we are talking about p-n junction, let us first clear our basics of what a p-type material will contain and what an n-type material will contain. We have seen how a junction is formed. We are taking a p-type material, we are taking an n-type material and we are using different methods to form the junction. But what exactly is there in a p-type material and what exactly is there in a n-type material, that we'll understand before discussing more about the p-n junction and its working. So in a p-type semiconductor, it is formed by doping with a trivalent impurity. Trivalent impurity means those belonging to the third group. Tri means three. Those elements which have three valence electrons, we call it as a trivalent impurity. So we are going to add a trivalent impurity, an impurity which is from the third group like gallium, indium, to a pure semiconductor. Now what happens, as the accepted trivalent atoms have only three valence electrons, which is added to a pure semiconductor like germanium and silicon, which has four valence electrons. So what we are doing here, we are taking germanium or silicon, which is having four valence electrons, and to that we are adding gallium or indium, which is a trivalent impurity which has three valence electrons. Then what happens here is 4 plus 3, when they are forming the covalent bonds, so only 3 electrons can bond with the 3 valence electrons of germanium, and 1 electron or there is lying idle without pairing. Okay, so there is always a deficiency of electron, which we call it as hole. So holes or vacancies are created for each acceptor or dopant atom. The dopant here is the trivalent impurity that we are adding. For every dopant, there is a hole or a vacancy that is generated. So therefore, what we understand here is holes are the majority. So whenever we are discussing about a p-n junction and its working, I will always say in terms of, in case of p-type material, holes are the majority carriers. Why holes are majority carriers? This is the reason. Because of the formation of holes or vacant sites. Now when we are taking an n-type semiconductor, it is doped with a pentavalent impurity. So pentavalent impurity here means an impurity which has 5 valence electrons, means 5 electrons in its outermost orbit, and they are from the 5th group. So the examples are arsenic and phosphorus. We have taken examples here, and now they are added to pure germanium or silicon. So as we have seen in p-type, we will discuss in n-type also. Germanium or silicon are having 4 valence electrons. They belong to the 4th group. To this we are adding a pentavalent impurity. Pentavalent impurity means which have 5 valence electrons in the outermost orbit. We will take either arsenic or phosphorus. So this has 5 valence electrons. So when we are adding a pentavalent impurity, what happens? These 4 electrons will form covalent bond with 4 of the valence electrons of arsenic or phosphorus, and 1 electron is left out without pairing. So there is always an extra electron that is left. So what happens here is extra electrons are created for each donor atom. In case of p-type, holes are generated, or holes are nothing but vacant electron sites. And in case of n-type, extra electrons are created. Therefore, we say electrons are the majority carriers in n-type, and whereas holes will be the minority. Now let us see the formation of the junction. What happens when two separate semiconductors P and N? We have seen we'll use any technique which we have discussed, we will use and form a junction. See here, this is the p-type and n-type brought together. Okay, so this is a p-n junction that is formed. This is a junction that is formed when they are brought together using different techniques. Now in a p-type semiconductor, whatever these white dots you see, they are the holes. So these represents the holes, and here you can see the black dots, they represent the electrons. So just now we have seen, whenever we are talking about a p-type semiconductor, holes are the majority carriers, electrons will be minority here. And in n-type, electrons are the majority and holes will be the minority. So p-type has holes as majority and electrons as minority, while n-type will have electrons as majority and holes as minority. This is what we need to understand from this diagram. The diagram clearly shows the holes in the p-type, which are a majority, and electrons in the n-type. Now what happens when they are brought together? As n region has high electron concentration and p region has high hole concentration, electrons diffuse from n side to p side. We have already discussed this term, diffusion. What is diffusion? We have seen always it is the movement of charge carriers from higher concentration to lower concentration. Now, we have seen the formation of a p-n junction where the holes are the majority carriers and the electrons are the majority carriers on the n side. Now, because on the n side electrons are in majority and p side electrons are minority. So, these electrons will always move from higher concentration to lower concentration. Means they will come from n side to the p side. So, this is how they are diffusing from higher concentration to lower concentration. So, this gives rise to diffusion current. So, whenever there is movement of electrons, so you will have the current, and this current we call it as diffusion current. Now, in the p-n junction, when electrons and holes are moving on to the other side, they will be leaving exposed charges or dopant atom sites, which are fixed to the crystal lattice and are unable to move. Means, here if you see in the diagram, so the holes that have come from the n-type to the p-type because of diffusion, what they do is they will leave positive vacant sites here, and we will call them as immobile ions. No? Because the electron has moved from here, this site will be a positive ion site. The same way here, wherever the holes have moved, you will have negative ion sites. So on the n side, what we are seeing is the positive ion cores, and on the p side, we see negative ion cores that are exposed. Now, because of this separation of the positive ion cores on the n side and the negative ion cores on the p side, an electric field is developed between the positive ion cores and the negative ion cores, and we are representing the field like this, positive and negative. And this electric field, what it does is, it will sweep out all the free carriers in this region. From this region, it will sweep out all the carriers, and this region will be depleted of charges. It will be free of charges. So what is there in this region is only positive and negative ion cores. Now all the free charges are swept out because of the electric field. So what we call this region is a depletion layer. So what is a depletion layer? A depletion layer is a layer where it is depleted of all the charges. There are no charges. It will have only immobile ions, positive and negative ions. And the thickness of this region is very small. It is of the order of 6 into 10 power minus 6 centimeters. Now, a barrier potential is formed due to this electric field. So now, because of the positive ion sites and the negative ion sites here, so we have seen that then electric field is developed. Now, because of this, there is no further movement of electrons from the n side or holes from the p side. Means there is a barrier that is formed at the junction. So we call it as a barrier potential or the junction barrier. And this barrier will not allow the further movement of electrons and holes from the N side and the P side. So, as the diffusion of the charges continues, negative ions form a layer of negative space charge region along the P side, and similarly a positive space charge region is formed by the positive ions on the N side. So, what we are seeing here is, when we are talking about N-type region, there is a positive space charge. This is the positive space charge that is formed on the N side, and here on the P side, there is a negative space charge that is formed. So, when this negative space charge and positive space charge are formed, this positive will prevent or will obstruct and act as a barrier for further movement of positive charges or holes. And the same way, these negative ions or negative space charges will form a barrier for the further movement of holes and electrons. So, there will be no movement of electrons and holes at equilibrium. So, then what happens? The positive space charge attracts the electrons from the P side. So, now if you see the scene here, if this is P-type, on P-type, what we have is the negative space charge region, and on the N side, what we have is the positive space charge region. And from N-type, the electrons are going on to this side, and from P side, the holes are coming on to this side until the barrier is formed. And we have called it as electron diffusion. But once the barrier is formed and equilibrium is reached, there is no further movement of electrons and holes on to either side. So then what happens here is, the positive region will attract electrons from the P side. But electrons are the minority carriers on the P side. So, if you see here, in the P side, there will be electrons which are minority carriers. They are being attracted towards the positive charge here. So, the electron drift we call. Electrons are the minority carriers on the P side, and they start drifting towards the N side because of the positive charge region here. And the same way, we have negative space charge region here. So, the holes will drift on to the P side. So, we have holes drifting from N side to the P side, and we have electrons drifting from the P side to the N side. And this gives rise to drift current. Okay. Now, if you see the direction of diffusion current and drift current, it will be opposite in direction. This is the hole diffusion and this will be the hole drift. They are opposite in direction. If this is in this direction, diffusion, and drift will be in this direction. Same way, electron diffusion is in this direction from N to P, and here the electron drift will be in the opposite direction. So, the diffusion current and drift current flow in opposite direction at one instant, and they both become equal. Now, let us move on to understand the IV characteristics. So, IV characteristic curves are nothing but current voltage characteristics. I stands for the current and V stands for the voltage, or we may simply call them as IV curves. Characteristic we may use or may not use. You call them as IV curves or IV characteristic curves of an electrical device. They are a set of graphical curves which are used to define the operation of that diode in a given circuit. So, when you see the IV curves, you can understand its operation, how a diode is operating. So, as the name suggests, it's a relationship between the current flowing through the electronic device and the voltage that is applied across the terminals. So, whenever we are applying a voltage, how the current is varying, we are going to plot a graph, study the graph and understand the behavior of the diode in an electronic circuit. So, the current voltage characteristics tells us much about its operation, and it's a very useful tool in determining the operating characteristics, at what values we can operate it. That becomes very clear from these curves. So this shows the possible combinations of current and voltage for a particular device. So for different devices, we may operate it at different voltages and see how the current flows. And also they are like a graphical aid. Always the graphical aids, what they help us is to visually understand better what is happening inside a circuit. Now first let us discuss the forward characteristics. So what are forward characteristics? It is the study of variation in current through the diode with respect to the applied voltage when the diode is forward biased. Forward biased here means, if you see, this is the symbol for a PN junction diode. No? So whenever we are have to put a PN junction diode, we use symbols. So this is the symbol for a PN junction diode. I'll say this is positive or P side, and this is negative or the N side. So now if you see in the circuit here, what we have here is a PN junction, and external resistance is also used to limit the flow of current. So this is the resistance R we are using to limit the flow of current. And we have a voltage, no? So 0 to 12 volt supply we are giving, and this is variable. This arrow denotes that it is a variable voltage supply. So whenever we are connecting a PN junction diode to an external supply, if the P side or the positive side of the diode is connected to the positive of the external supply, then you call it as forward bias. So why forward biasing we are going to discuss in the next lecture. Why do we need biasing? What are the different types of biasing? Because we are coming across this term, I just want to know, I want you to understand what a forward biasing is. So we have connected a positive of the PN junction to the positive of the supply. Then we say that the diode is forward bias, and you have a resistance to limit the flow of current. And this is a milliammeter which is used to measure the current. So when we have to plot the IV characteristics, so I stands for current and V for voltage. So you need to note down the current as well as the voltage. So a voltmeter is also connected across the diode. Now the forward bias voltage and the corresponding forward bias current are noted. So for different values of voltage, we will note down the values of current. And then you plot a graph. So how do we plot the graph? We will always take the voltage along the x-axis. So if I say this is the graph, this is the x-axis. So along the x-axis, we are taking the voltage V. And along the y-axis, we take current. Current we are measuring in milliamperes. So I milliampere. We are calling it as forward voltage and forward current because we have connected it in forward bias. We have connected the diode in forward bias. So we have the forward current and the forward voltage, and obviously that will be in the first quadrant. Now the graph is called the VI characteristic of a PN junction diode. This is how the graph looks like. So we are going to discuss about this graph. Why the graph is like this, why it is not a straight line, what is happening at different voltages, we are going to discuss. So we can have three inferences can be brought out from the graph, three main inferences. What are they? The first one, at room temperature, a potential difference equal to the barrier potential is required before a reasonable forward current starts flowing across the diode. So what we have seen in a PN junction diode is, when we are having a P and N, on the N side we were having the positive ion cores, and here we have the negative ion cores, because of which there is an electric field that is developed, and this is the depleted region, which is depleted of charges, which prevents the further movement of electrons and holes. Now, if we want the current to flow across the junction, we need to give external supply. So what did we do now here is, we have connected P to the positive and N to the negative. This is the external supply we have given, positive and negative. So P to positive and N to negative. This explains the forward bias. Now, minimum voltage, which we call it as a threshold voltage or the cut-in voltage or the knee voltage, is required for current, a reasonable current to flow through the circuit. Now, if you see here, if I take this as the origin, now as we increase the voltage, here if you see, the current is almost nil. There is no current. Why? Because of this barrier. No, because of the barrier, the electrons and holes are not able to cross the junction. There is a potential barrier across the junction which stops the movement of charges, and because of that there is no current. So even if you increase the voltage, there is no current. And at a particular voltage, this particular voltage, which we call as knee voltage or threshold voltage, the current starts rising. Okay, so what happens here is, this barrier is breaking down. No, the removal of the barrier causes the rise to the flow of current. So for different materials, this D voltage is different. So it is 0.3 volt for germanium and 0.7 volt for silicon. Means if I am taking a silicon diode and keep on increasing the voltage, only after a voltage of 0.7 volt, I will see a sharp rise in current. And the same way, if I take germanium, after 0.3 volt, there will be a sudden rise in current. And this current flow is negligible when compared to the applied voltage, when the applied voltage is less than the threshold voltage. So that is what we have discussed. So whenever the voltage is less than the threshold voltage, the current is small or negligible. And beyond the threshold voltage, the increase in current is significant. That means even for a small change in voltage, there is a sudden rise in current or a large current flowing through the diode. Now, what is the second inference? So, the graph clearly says that the current flow is not linear. It is not linear. It is not straight like we see in Ohm's law. So, in Ohm's law, what we see whenever we are plotting a graph for V versus I, it will be a straight line. No? So, V is proportional to I, directly proportional to I. This is what we see. But in this case, it is not a straight line. No? It is exponential rise. This shows that it is exponential rise. And it does not obey the Ohm's law. Now, the forward resistance R of the diode can be calculated with the help of this. How do we calculate the forward resistance RF? RF is equal to delta V upon delta I. So, I can write it as RF is equal to V2 minus V1 by I2 minus I1. This is again coming from our Ohm's law only. V is equal to IR. So, if I want R should be definitely equal to V upon I. No, it is not obeying the Ohm's law, but we can calculate the slope of the graph using this V2 minus V1 by I2 minus I1. This gives us the forward resistance. For a small change in voltage, there will be a small change in current, which we may also write it as delta V upon delta I. Now coming to the reverse characteristic. So when do we get reverse characteristics? When we connect the diode in reverse bias. This is reverse bias. What is reverse bias? We take the diode, PN junction diode, and how we connect it to the external supply. The positive of the diode is connected to the negative of the external supply, and the negative is connected to the positive. So, in reverse bias, the P region of the diode is connected to the negative terminal of the supply, and the N region to the positive terminal of the DC supply. That is what we exactly see in the figure. So in reverse bias, this is the figure for reverse bias. So in reverse bias, we have connected the positive to the negative and negative to the positive. This resistance is always there, which limits the flow of current. We have an ammeter to measure the current, and we are using a microammeter. Micro means 1 microampere is 10 power minus 6 ampere. Micro is 10 power minus 6 because the amount of current in reverse bias is very small. So we measure it in microamperes. We use a microammeter here directly. And then we have a voltmeter to measure the voltage because we need to draw the voltage current characteristics. So we also need to measure the voltage. So the voltmeter, which is connected across the diode which is connected in reverse bias. So now we will note down the values of voltage. For different values of voltage, we will note down the values of current. And then a graph can be plotted which gives us the reverse characteristics or reverse bias characteristics we call for a PN junction diode. So this is the figure and this is the graph. Now if you see here, what we are doing, we have connected it in reverse bias. So the voltage applied will be negative and the current also will be negative. So minus V. So we are taking it along the negative x-axis and we take this along the negative y-axis. So in reverse characteristics, the graph will be in the third quadrant because we have to consider minus V along the negative x-axis and minus I along the negative y-axis. Now, what we do is, as you increase the voltage, so how the current is varying, we are going to see. So, under this bias, a very small current in microampere flows across the junction. And this is due to the flow of minority charge carriers, which we will call it as leakage current. The current in reverse bias is very, very small. And because it is very small, we call it as leakage current, which is due to the minority charge carriers. And besides, current is also independent of the voltage. Now, if you see here, what we have seen in the reverse bias voltage can be increased only up to a rated value. What happens here is, even after a certain value, if you are trying to increase the voltage, so there will be a breakdown, means the diode may break down and it may not be useful further. You cannot use the diode again. So whatever we do is, it has to be operated within the breakdown region. So what happens if you increase the voltage further, it will enter into a breakdown region. So if the applied voltage is increased beyond a rated value, it will produce an extremely large current which may destroy the junction due to overheating. So if you are increasing, what happens? There may be large current, but the diode gets damaged due to large amount of heat that is produced. And this is called as the breakdown of the diode. And the voltage at which this breakdown occurs, we call it as breakdown voltage. So whenever we are using a diode, it is very important for us to understand or to know what is the breakdown voltage. So whenever you try to use it above that particular voltage, the diode breaks down or it may get destroyed due to overheating. So it is always safe to operate a diode within the threshold voltage. That is the breakdown voltage. I may not call it as threshold voltage. For the positive, we have said it is knee voltage or threshold voltage. Here we call it as a breakdown voltage. Now let us look at both the characteristics together. So in forward bias, what we have seen is, we have plotted voltage along the positive x-axis and current along the y-axis. For small values of voltage, until the barrier is breaking down, now there is no rise in current. But once there is a barrier breakdown, no, the barrier. We will call this as the knee voltage or the threshold voltage, above which there is a sharp rise in current, or we say it is an exponential rise in current. So we are calling this as a forward bias or the forward characteristics, which is in the first quadrant. Now when we see the reverse bias, when we have connected the diode in reverse bias, we are considering the negative x-axis, we have taken the voltage, and the negative y-axis we have taken the current. And because the current is very small, we are measuring it in microampere. And so as you increase the voltage, there is a very small rise in current. At one point, the current may increase, but the diode will break down. So we are making sure that the diode is always operated within the breakdown region. So we will not go beyond the breakdown region because the diode will be of no use. So for reference for this topic, you may refer to Semiconductor Physics and Devices by Donald A. Nieman by Tata McGraw-Hill Publications, or you may also refer to Semiconductor Devices, Physics and Technology by Simon Z. and Ming-Wei Lee. Or you can also refer to the third book, but at a later stage. So for this particular topic of VA characteristics and PN junction diode, you can refer to these two books, and I have given the citations on the slide also, so which you can refer to. Thank you and see you.
Like, share and subscribe. Hit the bell icon for more updates.